Hi, I'm Guillaume. I work for ARM. I'm also part of the Veracruz project, which is a project adopted by the CCC. And today I'd like to talk about the intersection between confidential computing and DPUs, also known as data processing units, also known as SmartNICs. So there's been lots of efforts towards making confidential computing more useful. For example, we moved from in-process enclaves like SGX to blind hypervisors like AMD-ACV. But confidential computing is still mostly restricted to the CPU, hence to general-purpose computations. To give you an example where confidential computing, as we know it today, might fall short, let's just imagine what confidential ML training would look like in the cloud. If a machine learning company wanted to outsource the training to the cloud today, they would have to trust the entire machine learning data center. So not just CPUs, but also AI accelerators, network interfaces, storage devices, and so on, which are not equipped with hardware-based enclaves. So we can see that this current limit could be detrimental to the wider adoption of confidential computing, particularly in the data center. So in this work, we've been exploring what confidential non-CPU-centric devices could look like. And as a first step, we started at the infrastructure level with the DPU, a device with a strong affinity with multi-tenant environments. DPUs are part of the trend of offloading specific tasks onto specialized yet programmable hardware. So just like GPUs are good at processing parallel tasks, DPUs specialize in infrastructure functions, which are everything but guest workloads. So if you take AWS, for example, that would encompass I/O-driven overheads such as VM-to-VM communications, VM communication with the outside, file system operations, etc. Among other things, they boast high-throughput networking. We're talking about 400 gigabit per second on the latest models. They also can accelerate cryptography and emulate storage devices over the network. And they're doing all that more efficiently than traditional server CPUs. We're talking 20 to 25% energy savings in telecoms data centers, for example. DPUs come in lots of forms and shapes in a spectrum of solutions ranging from CPUs to ASICs, which induces fragmentation, as you can imagine. They typically consist in an SoC with the following components: a CPU subsystem for general-purpose tasks and management of the system, a high-performance NIC or several high-performance NICs, hardware accelerators, so as we discussed before, some for crypto, packet processing, and so on, and a PCIe switch to interconnect all these components, not just on the SoC itself, but also between the DPU and other devices. Okay, let's now talk about the cool things we can do when combining confidential computing and DPUs. So the first use case we identified is vicarious attestation. And the idea is that if a node A trusts a node B and a node B trusts a node C, then by transitivity, node A can trust node C. So the idea is that we could use DPUs to take care of attesting other nodes on the network on behalf of its host. We would thereby pave the way for the creation of a trusted network of nodes that could take the form of a VPN or a virtual private cloud. The second use case, which can complement the first one, is confidential offload of network functions. So if the host already trusts the DPU, then it can offload, for example, TLS, which could include handshake, record protection, maybe even some TCP logic, to the DPU. And since the TLS connection would terminate in the enclave, then it would mean that the plaintext would be made available securely inside the enclave for further processing, for example, detecting threats, enforcing any kind of policy, or mitigating data leaks. A threat model for interfacing host and DPU could look like this. On the right, an enclave running on the host establishes a secure channel of the TE running on the DPU on the left, leveraging TDISP, a protocol based on PCIe, with a flow very similar to attestation and TLS. Additionally, any accelerator and security component used by the offloaded workload would have to be attested. Note that the threat model would vary a lot across different DPUs. Also note that devices supporting TDISP are not widely available, and if they were, the architecture would vary widely across manufacturers. We developed a framework to easily build and deploy hosts and DPUs. It supports verbs to attest and provision codes to other nodes. Our setup consists in BlueField-2s on the DPU side and ARM Neoverse CPUs on the host side. Evaluation is still in progress, but feel free to check out the project on GitHub.